The last line in the square of each element on the periodic table is the precise description of the electron configuration of the element. These letter symbols refer to the electron orbitals, specially shaped regions where we might find electrons moving around the nucleus. Chemists are mainly concerned with the orbitals of the valence electrons because they determine how atoms bond together and the chemical behavior of the element. There are four important orbital shapes: S, P, D, and F. The s orbital can take a maximum of 2 electrons. The p orbitals can take up to 6 electrons. The d orbitals can take up to 10, and the f orbitals can hold a maximum of 14 electrons. There is a direct connection between how many electrons it takes to completely fill the orbitals at each energy level and the number of elements in that period of the table. Let's look at some examples of how the electron configurations of atoms are written. Hydrogen has only 1 electron in an S-shaped orbital. It is written 1s1. Helium has 2 electrons in an s orbital. It is written 1s2. This is saying in the first energy level the S-shaped orbital is filled to capacity with 2 electrons. Lithium has atomic number 3 and is in the next period of the table. But look how its electron configuration is written. This is a shorthand that chemists have developed. He says that the electrons in the inner energy level are exactly like the electron configuration of helium. 2s1 is a description of the valence electrons. It is saying that in the second energy level, the S-shaped orbital is half filled with 1 electron. Reading electron configurations takes some practice. Let's read one more. Gold. The inner energy levels have the same configuration as the noble gas xenon, whose symbol is Xe. The valence electrons are the following: 14 electrons in the 4th energy level in f orbitals, 10 electrons in the 5th energy level in d orbitals, and 1 electron in an s orbital in the 6th energy level. It was only when chemists understood the electron configurations of elements that they could understand how atoms interact to make the millions of substances that we find in the universe.